So first of all, I'd like to thank the organizers for inviting me here today. Thank you guys, and thanks everyone for coming. So a little bit about my background. I am a PG student at Biomedical Imaging Group Rotterdam, where we do all sorts of research about medical image analysis, specifically how to apply AI to medical image analysis. And my PhD topic is centered around weekly and semi-supervised learning methods for medical image analysis. So actually, most of my research was focused on these topics. However, around 2 years ago, we had an internal hackathon of sorts, and it was there where I came up with this method that I'm going to talk about today, with the adversarial heart attack. So, and it was so fun that I got kind of sidetracked into researching adversarial attacks, and I did another project about it, which was about factors that affect transferability of adversarial attacks. So that is factors that affect how well adversarial attacks made by one network work on another network. And more specifically, we looked at how ImageNet pre-training affects this transfer, and how differences in training data between networks affect transfer of adversarial examples between those networks. So let's get to the adversarial heart attack. So this image on the slide is basically the synopsis of what it is. So we have a network that was trained to segment heart, lungs, and clavicles in chest X-ray images. So this image here shows predictions made by this network. So the blue is the heart, and green and pink are the lungs. And what this adversarial heart attack does basically adds this very special adversarial noise that shapes segmentations predicted by the network in this way. So instead of heart shape, which is kind of round, now we have this beautiful heart symbol. So before explaining how the heart attack works, I wanted to give a bit of a background about adversarial examples. So an adversarial example is an input signal to a deep learning algorithm, or it can be actually any sort of machine learning algorithm, which is perturbed by a very special noise, which is engineered to change the predictions of the network or whatever targets machine learning algorithm. And so here on the slides is an example of adversarial examples from computer vision. So all these images are classified correctly by the network, but if we add this very subtle, almost imperceptible noise, the network starts to classify everything as ostrich. So, and adversarial attacks were very successful when applied to networks trained for a very wide variety of tasks. So, adversarial attacks against medical image classification and segmentation networks are quite successful. So adversarial attacks, like there are very many different types of them, and one way to categorize them is into untargeted versus targeted. An untargeted attack is an attack that simply tries to disrupt the network predictions. So it tries to make the network output something wrong, and it doesn't really matter what kind of wrong it is. So this image on the slide is an example of an untargeted attack against a segmentation network. So the right side of the image is perturbed by this attack, and you can see that segmentation is sort of messed up. And apart from untargeted attacks, there are also targeted attacks, and they aim at changing predictions of the network in a specific way. So they make the network predict a very specific class or segmentation. And here's an example of a targeted attack for the same application. So this is the prediction of the network with respect to the clean image. And for adversarial example, the prediction given by the network is a segmentation with respect to a different image. So now I would like to talk a bit about how adversarial attacks work. So here on the slide is an equation that corresponds to one of the simplest adversarial attack methods. So it's also methods that was probably the first to be introduced for deep networks. So it's called fast gradient sign method, or FGSM. And how we compute adversarial image is basically to clean image we add adversarial noise, which is modulated by a parameter that regulates the magnitude of this noise. And the noise is simply the gradient of the loss function with respect to this example, with respect to the input of the network. And for FGSM, it's actually not just the gradient, but the sign of the gradient. So what's going on here is that we're trying to perturb the input of the network in such a way to maximize the loss function and thus minimize uh, uh, yeah minimize the match between the predictions and the ground truth. Then there is also an iterative version of FGSM, which is far more powerful in terms of the results. So, and it's basically just an iterative application of the simple FGSM. So it's an iterative computation of the gradient and adding it to the image. And so this procedure is very similar to how we optimize the weights of the network. So we optimize during training the weights of the network so that we get specific predictions with respect to our training images. And this basically optimizes the input to the network so that we don't get a specific prediction. And so this formulation corresponds to an untargeted iterative FGSM. And to get a targeted iterative FGSM, we need to change only two things. So first of all, we need to change the direction of optimization. So instead of maximizing the loss, we want to minimize it. And then we need to compute the loss not between predictions and the ground truth, but predictions and the target label. So like we're going into the direction that minimizes the mismatch between the predictions and the target label. So adversarial heart attack is based on this targeted iterative FGSM. And one thing that we need for this heart attack is the target segmentation, and that we get just by computing the center of gravity of the heart and placing heart symbol in there. And we use that as a target for iterative FGSM. So like a small note on how this algorithm works. So we don't only optimize the noise so that the predictions with respect to the heart channel change, but we also optimize the noise so that the predictions with respect to the other classes stay close to the ground truth. And that's because we noticed that when we only include the heart channel in the optimization, that disrupts segmentations of other structures around the heart. So the best results we get when we include all classes into the optimization. So how does this heart attack, how well does it work? So basically, with enough of noise, which still looks very subtle, it works very, very well. So with this amount of noise, so it's epsilon equals to 0.04, like this is the maximum amount of noise that can be added to a single pixel. And like the intensity of the image is somewhere between -1 and 1. So it is pretty subtle amount of noise, and it works very consistently. So this is not a cherry picked image. It works very well in most of the images. So then we tried this attack with a larger heart, and that worked more or less well, but in a significant proportion of the images, we had this problem. The problem was extending the card class far into the LAN. So this didn't happen in most cases, but it did happen often enough. And another thing we notice is that with smaller epsilon, the hard segmentation is extending into these regions that have a very similar intensity to the heart, but not to the lung regions that have very different intensity and texture. So it sort of seems that extending segmentations of an organ into regions that have kind of similar visual quality is easier than extending it into regions with very different appearance. So another thing that we noticed, so we looked at the adversarial noise that our heart attack produces, and we noticed that it modifies pixels that are quite far from the heart, and that happened even when we only optimized for the heart class. And so at first, it seemed like a little bit of an odd finding, but I think it has a very simple explanation. So the heart attack also tries to maximize the confidence with respect to non-hard voxels. And then if we zero the noise, which is further away from the heart than half of the receptive field, then the heart shaping is not really disrupted, which is how it should be. However, we also tried to zero the noise that's outside the box that encloses the heart, and that does disrupt the heart segmentation. And so that means that the heart attack changes the voxels that are around the heart in order to change the segmentation with respect to the heart voxels. So another experiment that we did was with black box adversarial heart attack. So a black box attack is an attack scenario where the attacker doesn't know at least the parameters of the network, and they may also not know like what architecture it has, etc., etc. So for this experiment, we had a different network with the same architecture, same training parameters, same loss function, etc., and trained on almost the same data. So there were very minor differences in the data. The validation set was a different random subset of the same data set, and the training sets were, yeah, maybe a quarter of the images were different or so. And the black box heart attack completely failed. So for smaller amounts of noise, it basically didn't change the segmentations much, and for a larger amount of noise, it completely disrupted segmentations of the heart and other structures. And another experiment that we did is with a different kind of attack. So this attack resized segmentation contours of the heart and also the other structures. So like we enlarged it and shrank it by quite a large amount. And generally that worked pretty well, but there were a few problems, and we had a few observations that were made by just manually looking at the predictions of the network with respect to adversarial examples. So we had again this problem with extending hearts far into the lung. So it's like kind of the same thing that we got with the large heart. Another thing we've got with trying to enlarge lungs, so maybe you cannot see it so well, but this region here in the target segmentation should belong to the lung, and the lung segmentation stops here and does not extend here. And this happens in almost all or all images that we have seen. And one last finding happened when we tried to make clavicles smaller. So in the target segmentation, this region immediately around the clavicle, like where the actual clavicle is background, but yet it's still predicted by the network as the lung. And it happened also very consistently. So like in most cases, in most images that we have seen. So it sort of seems like the network really tries to keep lungs and clavicle adjacent. So that was it for the results. So what conclusions can we draw from all these experiments? So targeted manipulation of segmentations of medical image analysis networks is generally quite successful with rather low amounts of noise, and it's successful even when the target segmentations have completely implausible anatomical shapes. So it seems like the network really has no problem to segment a heart symbol instead of a heart shape. However, we noticed that some manipulations are harder than others. So we have seen this thing that extending heart class into the far into the lung didn't always work very well, and extending lungs into background areas that are outside the body of the patient also didn't work very well. So, and if we extrapolate this a little, like if we generalize this a little bit, so it seems like extending contours of organs into regions with intensity or texture that are not characteristic of that organs is harder. But then again, that didn't happen in every case. So, for example, when we trying to make land smaller, then like the texture and intensity of the land is not very typical for the background class, and yet there seem to be not so much problem to extend the background into this region. So it sort of seems like the network has learned something very well, like that this regions outside the body of the patient cannot be learned. So it has learned these things well, but other things it has learned less well. So, and second sort of pattern is that changing segmentations into target segmentations that violate adjacency priors between classes can be more difficult. So we have seen this that the network tries to keep LAN and clavicles adjacent, but it also was not like this in every case. So, for example, making heart smaller was no problem, although heart should be adjacent to LAN in these regions. So, and the last finding is that black box targeted attacks are challenging, and this finding is very much in line with the rest of research on black box targeted attacks. So black box attacks are in general quite difficult, and targeted attacks are even more difficult. But then again, we didn't use the most powerful algorithm for black box attacking, so that there are ways to make targeted adversarial examples more transferable. So it is maybe possible that heart attack could be improved to be more transferable between networks. Um, so yeah, that was that. The paper that describes this project is on archive. So if you would like more figures or some quantitative results, then you can check it out if you'd like. Yeah, thank you for your attention.